A year ago, I made this 3D engine in C++ using SFML. SFML is a 2D graphics library which runs completely on the CPU. It has some support for shaders that will run on the GPU, but it's not really ideal for working with 3D graphics. Because it was all on the CPU, the engine was pretty slow, so I couldn't render anything too fancy, and I couldn't go crazy with the lighting. I was able to add some simple lighting with diffuse lighting and specular highlight, but it's not as visible in the video, but a lot of this lighting was incorrect and broken. So recently I decided to revive this project, and this time I would be making it with opengl so that I could access the graphics card through shaders. This would make it a lot faster and also give me the capability to add a lot more features to this 3D engine. I started out by adding a simple projection matrix, and I also added transformations, meaning you can move the object around or rotate it. I did both of these things using homogeneous coordinates. I also added a simple obj file parser so that I could load any 3D models that I wanted to from any 3D modeling program. This is the projection matrix that I used. What a projection matrix does is it transforms a 3D coordinate and it projects it onto a 2D plane, meaning we can get the 2D position of that 3D coordinate on our screen. So the reason it's 4x4 is because, like I mentioned earlier, I'm using homogeneous coordinates, and to transform those, you need to multiply by a 4x4 matrix. In this projection matrix, the variables are A, which is the aspect ratio or the screen width divided by the screen height. Then far near are the far near clipping planes. This means is for the near clipping plane is how close do objects have to be to the camera for them to get cut off. The reason we do this is because we don't want to be drawing anything that's behind the camera, because we can get weird artifacts if we do that. And then far is the same idea, except it's how far does an object have to be for it to get cut off. The FOV is just the field of view, which is the angle between the camera and the projection plane. And for calculations in the projection matrix, the top left two, what they're doing when they're doing the FOV divided by 2 and the tangent of that is they're trying to get the focal length, because the focal length is the distance from the camera to the projection plane. So we're dividing that FOV by 2 and then getting the tangent, which if we do 1 divided by that, we get that length because 1 is the screen width in opengl coordinates. And then the calculations in the more bottom right section are for those far and near clipping planes. I used a similar method for transformations. I also used 4x4 matrices and multiplied them by the homogeneous coordinates. And this allows me to do both translation, which is moving an object's position, and rotation of the object around its origin in one transformation. The way this works is the matrix first has the rotation section and then also translation. So first I need to calculate the rotation matrix. As you can see in the top, these are the 3 matrices, which are the rotation matrices around specific axes. So there's the x-axis, y-axis, and z-axis. Then to get the full matrix, and then also because the final result is 4x4, we also have the 0, 0, 0 at the bottom, then the bottom right is 1, and then 0, 0, 0 in the right column. Then to get the full rotation matrix, we just multiply those matrices. So we do x times y times z. And then the translation element, we just need to add to those 3 zeros in the right column. So I just add this matrix, which has mostly zeros, and then just x, y, z in the right column. I hard-coded this in my program for speed, but this is what the mathematical way would be. And if I were to multiply any coordinate with 4 values, what homogeneous coordinates are is where it's just x, y, z, and then it has a w, which is usually 1, or it can be 0 as well. When I multiply this matrix by that homogeneous coordinate, it will both move that coordinate's position by the specified x, y, z, and also rotate it the theta number of radians or degrees. This model is supposed to be the head of a monkey, but it's still kind of hard to tell. The main reason is that there's no culling. This means that you can see through the monkey and you can see triangles on the other side of the model. So to fix this, we need to calculate the normals for each triangle and then see if those normals are facing the camera or facing away. If they're facing away, we don't draw that triangle. So this is what it looks like with culling. As you can see now, you can't see the triangles on the other side of the model, and the model's a lot more recognizable. You can actually tell that it's a monkey. I also added a depth buffer. What this does is it makes sure that pixels farther away from the camera are drawn first, so that if there's like the head of the monkey is behind the ear, it makes sure that the ear is drawn above the head of the monkey instead of the other way around, so that it looks normal. The reason everything is different colors is because right now I'm just setting the color equal to the normal of the triangle, but once we add lighting, we will fix this. Like I said earlier, calculating culling is pretty simple. If you have a vector n, which is the normal of that face, and then a vector c, which is a vector pointing from that face to the camera, we can calculate the dot product of the two vectors. If the dot product's positive, we know that that face is facing towards the camera and that we can draw the face. But if the dot product's negative, that means they're facing opposite directions, meaning that face is pointing away from the camera, which means we don't need to draw that face. This is what culling looks like in the shader. This is the geometry shader, which I will explain the type of shaders later on. First, we get the 3 coordinates of the triangle, A, B, and C, as you can see in the top. Then we calculate vectors for 2 edges of the triangle. So we just do B minus A and C minus A to get the 2 edges. Then to actually calculate the normal, we get the cross product of those 2 edges, which basically gives us a vector perpendicular to those 2 edges. And then we normalize it. And then the actual culling part, first, we get a vector pointing from a vertex to the camera. In this case, I just use the A vertex. It doesn't really matter because the normals are the same across the entire triangle. So it's just whichever one you want. And then I calculate the dot product between that vector from the vertex to the camera and then the normal. And we check if that's less than 0, then we abandon drawing the triangle. But if the dot product is greater than 0, meaning the face is facing the camera, then we continue with the drawing. Before I move on, I want to explain how I made my shaders. Shaders are programs executed on the graphics card, which makes them very useful for calculating lighting, since lighting for lots of pixels can be calculated in parallel. Most shaders have 3 or 2 stages. In my case, I have 3. First comes the vertex shader. This vertex shader takes in the position of the vertices of the triangle, so 3. And what it does is it handles projection, transformations, being things like rotation and translation of objects, or also translating an object's vertices into camera space. And also it passes data that might be necessary for later shaders into the geometry shader. Next comes the geometry shader. The geometry shader is between the vertex shader and the fragment shader. It gets all 3 vertex positions at the same time, already projected, all of that. And what it does is, like I showed earlier, it calculates the normal and also the culling. And also if the vertex shader needs to pass things like texture coordinates or normals to the fragment shader, the geometry shader passes those things to the fragment shader. So what the fragment shader does is rasterization and lighting. Rasterization sort of happens between the geometry shader and fragment shader. What it does is if I have 3 vertices in the vertex shader, rasterization will interpolate those vertices. So in the fragment shader, I get a 3D position of each of those vertices, which is interpolated. And I can do that for anything. So for example, for normals, which I actually do this later in the video, but Normals I can interpolate using rasterization as well. So if I have different normals at each vertex, it will interpolate the normals so that it's smooth across the entire face. Also, the fragment shader handles lighting because the fragment shader runs for every single pixel in that triangle. The main reason we need rasterization is to interpolate the vertex positions. This allows us to get the 3D position of every pixel, which is very useful for lighting. So as you can see on the screen, right now I'm displaying the 3D position of every vertex as its color. So you can see that the pixels 3D positions are interpolated, so there's nothing clunky and you can't see the actual faces or anything like that. And this will be very useful for lighting later on, and I will use rasterization for other things as well later on. Now that we have the normals for every triangle and also the 3D position of every pixel, we can move on to lighting. The first type of lighting that I'm adding is diffused lighting. This is the simplest form of lighting. It's just calculating how much light is hitting a pixel. So to do this, what we're doing is we have a vector pointing from that pixel to the light source, and then also we have the normal of that pixel, or I guess triangle, but the normals over a triangle right now are the same. The calculation is really simple. We're just calculating the dot product between that vector from the pixel to the light source and the normal, which basically will just give us how close those two vectors are, how close the direction of those two vectors are. And based on that, we can determine how strong the light in that pixel is. So if the light vector is pointing really far away from the normal vector, that means there's no light in that pixel. So this is what it looks like added to the program. In this demo, the light source is positioned to the top right of the camera. And as you can see, the light is natural and correct. The faces, the pixels rather, that are facing more towards the light source are brighter than the pixels facing away. And also, the light isn't following the model as it rotates, which is good because that means that the transformations of our vertices and normals is correct and working. And the way this works in code is pretty simple. First, we get a vector from the pixel pointing towards the light source, which is just the light source position minus the pixel position, and then we also normalize it. And then to calculate the diffused lighting, we just get the dot product of the pixel to the light vector and then the normal of that pixel. The next type of lighting that I added was specular highlight. Specular highlight, unlike diffused lighting, is calculating how much light is being reflected into the camera. This means that the position of the camera will actually change the lighting on the surface of the model. So this is a simple drawing of what we're trying to do. The hardest part of this is calculating the reflection vector, which is the vector of the reflection of the light. So if we have a vector pointing from that pixel to the light source, we're trying to basically get the opposite, which is the reflection. And then to calculate the actual lighting, we can just calculate the dot product between that reflection vector and a vector pointing to the camera. So now I'm going to go through a quick explanation of how I actually calculate the reflection vector. So in this example, L is the vector pointing from the pixel to the light source, N is the normal, and then R is the reflection vector. The first thing we need to establish is that the length of the vector of L projected onto N is the dot product of L and N, and of course L and N have to be normalized here. Now that we know the length of L projected onto N, it's actually pretty simple to calculate the reflection vector. First, we get negative L, which is just the inverse of the vector from the pixel pointing to the light. You could also think of this as just the vector from the light pointing to the pixel rather than the other way around. Then if we go up two of those projected lengths, we will get to R. But we can't just add the dot product of L times N because negative L is a vector and the dot product of L and N is a number. And you have to remember that all of this is in 3D, not 2D. So in 3D, we can't just get a vector pointing up it's always going to be pointed in a different direction. But the normal vector is pointed in the right direction already, and the normal is already normalized. So if we do the dot product of L times N times the normal vector, and we do that times 2, we get those two vectors going up. So then to calculate the reflection vector, all you have to do is just negative L, which is the inverse of L, plus 2 times the dot product of L and N times N. Now that we have the reflection vector, it's really easy to calculate how much light is being reflected into the camera. If we have another vector called C, which is just the vector pointing from the pixel to the camera, we can calculate the dot product between C and R to get how much light is being reflected into the camera. And that's our specular highlight. To calculate the color of a pixel, what we can do is we have a base color, which is just the color. So for example, red, and this is RGB, so it would be 25500 times the diffused lighting. So each of those elements in the color is being multiplied by the diffused lighting, and then we add the specular highlight to each of those elements as well. This will give elements where there's more light reflecting into the camera a more white glow. This is what it looks like in code. So first we just get a vector pointing from the pixel to the camera, which is just the camera position minus the pixel position, and we normalize it. Then we calculate the light reflection vector using the formula we just derived. So it's again the negative L vector plus 2 times the dot product between the normal and the L vector times the normal. And then to get the specular highlight, we just calculate the dot product between the pixel to the camera vector and then the light reflection vector. And then we also multiply that by a coefficient just to determine how strong the specular highlight is. And this is what it looks like. As you can see, it's a bit more natural now. The light isn't as intense. It's not as red anymore. It's got a bit more of that actual light reflecting into the camera. It's a bit whiter, like in real life. Now that I had specular highlight, I actually wanted to add camera movement to see if it would change based on where the camera is. So I added camera movement. The way I did this is I used those same transformation vectors from before. So the camera would have an inverse transformation matrix. This would just be the inverse of its rotation and position. And then I would apply that matrix to all of the vertices in the shader. So there's no actual camera going around the scene, but instead I'm moving all of the objects around the camera so that it looks as though the camera is moving around. And this is how all these 3D game engines work. There's no actual camera. It's not magic. Everything in the world is just rotating and moving around the camera. So as you can see, it works pretty well. I implemented some simple controls so that I can control it from the keyboard. And you can see that the specular highlight, the brightness is kind of changing on some triangles based on where the camera is, and it looks pretty realistic. Like I said earlier, with when it was rotating, the lighting isn't following the camera or anything, meaning that we're calculating everything in world coordinates correctly rather than in camera coordinates, which is good. I then just downloaded some models and started messing around with rendering some different things. So here I'm rendering the Utah teapot. I added the ability to change the colors of the objects, and here they're just spinning. I then also remade my obj file parser to support a lot more complicated models. So this model that I'm showing here has around 1 million vertices, and the game's rendering it completely fine without any lag. It takes a bit to load, but Blender and all those other programs also take around the same time to load these kinds of models. Then I just tried downloading some more really high detail models and tried displaying them, seeing how they would work. So here I'll just show a few of those models. The next thing I did was add textures. Textures took me a while because I ran into a lot of bugs, and also parsing the obj files becomes a lot more complicated because of texture coordinates. The way textures work is each vertice has texture coordinates. These are the coordinates of the image which it gets the texture from. So that's from -1 to 1. And these coordinates are in the obj file, but they're not already correlated to the vertices, meaning the model's not baked already. So when parsing, I would have to correlate these texture coordinates to the vertice. But then it becomes more complicated because one vertice can have multiple different texture coordinates, in which case you have to make different copies of that vertice to store those different texture coordinates. But in the end, I was able to do it, and I think the result is pretty cool. Here's some examples of previous models and new models that I'm using with textures. The only drawback here is that I haven't implemented yet a way to load multiple textures. Lots of models will have different textures for different parts of the model or different textures that overlap, and that's a bit more complicated. I think I'm held back by the obj file format. I think I'm going to have to move on to something like the FBX file format or something like that, where I can get information about which vertices correlated with which texture or things like that. The last thing I want to implement into this 3D engine is normal interpolation. Normal interpolation allows the lighting to be a lot smoother. Right now, if we zoom into a model or even from far away, you can still see all of the triangles in the model, even if the model is really detailed. This is because of how the lighting works. The normals in a triangle are the same for each pixel in that triangle. It's just the normal of that face. And because of this, in the lighting, we get an effect where you can see all of the triangles. To fix this, we need to do something called normal interpolation. What normal interpolation is it smooths out the normals across that face. And to do this, we need to get a normal for each vertex. That normal will be the average of the normals of the faces that are connected to that vertex. So if you can imagine a cube, for a cube, the normal of a vertex will be the vector pointing as far away from the cube as possible. And once we have those normals for each vertex, what we can do is interpolate the normals through rasterization. This is the same way we rasterize the 3D coordinates. In our vertex shader, we pass in the normals for each vertex, and then it rasterizes or interpolates those normals in the fragment shader. So as a result, we get an interpolated normal in each pixel, which smooths out the normals across the surface. An easy way to imagine this, again, with a cube, if each normal for each vertex is pointing away from the cube, then the interpolated normals across will sort of look like a sphere. So this is what it looks like with interpolated normals. As you can see, when we zoom in, you can barely see the triangles. It's a lot smoother. It looks a lot more realistic. And even with low poly models, it will still look relatively smooth and the lighting looks a lot more realistic. Of course, those triangles are still there. We're not adding detail to it. We're just changing the lighting and shading so that it looks like there's no triangles there. So that's how my 3D engine works. I hope you enjoyed the video. I will leave a link in the description to my GitHub, which will contain all the code of this project. And also my GitHub will have links to all of the models I used in this video. Hope you enjoyed, and thank you for watching.